Welcome back. The frontier of AI right now, well, it isn't just about making models bigger, it's also about context length. We're talking training large language models, LLMs, to handle truly massive context windows. Think up to 1 million tokens. This unlocks some really powerful stuff like coding agents that can read multiple files or really long chain of thought reasoning. But scaling training up to that level, it's incredibly expensive and frustratingly slow. So that's our mission today. We're doing a deep dive into research that seems to have cracked a major performance bottleneck for this long context training. We're focusing on a new approach called core attention disaggregation, or CAD.
That difficulty you mentioned, the cost and the slowness, it really stems from a fundamental issue with the transformer architecture when you try to train it at scale. We call it load imbalance. You see, training these huge models means spreading the work over tons of devices, hundreds sometimes. But if those devices don't finish their piece of work at the same time, the whole system grinds to a halt, waiting for the slowest one, the straggler. And to really get why this happens, you have to look at the compute cost. The self-attention mechanism in transformers, it's the most expensive part. Its cost grows quadratically with the sequence length. So double the length, you quadruple the compute. We write that as all dill dollars. Everything else, like the feed-forward networks, layer norm, that stuff scales, well, much more nicely, roughly linearly. This mismatch is really the heart of the problem.
That quadratic versus linear thing is, it's crucial. It's like, imagine compute costs as meeting people at a party. The linear parts are like just walking in. But the attention, the quadratic cost, it's like having to introduce every single person to every other person there. If the party size doubles, the number of introductions just explodes. And this isn't just theory, right? This is why trying to scale up your training from, say, 64K context to 512K can just blow your cloud budget.
Okay, so let's look at how this actually plays out during training. A common technique is document packing. To keep the hardware busy, you take documents of different lengths and you basically smush them together into fixed-size chunks. Let's say every chunk is 4,000 tokens. It's balanced, right?
Yeah, on the surface. But here's the catch. Imagine two of those 4,000 token chunks. Chunk A is just one single document that happens to be 4,000 tokens long. Chunk B is, say, 4 separate 1,000 token documents packed together, still 4,000 tokens total. But because attention scaled quadratically, Chunk A, the single long document, needs roughly 4 times the attention computation, the FLOPs, as Chunk B. Hold on. Same total number of tokens, but 4 times the work. That's a massive hidden cost.
And in a big distributed system, that hidden cost creates those stragglers we talked about. If you're using data parallelism or DP, where each device has the whole model, well, the device working on chunk A makes all the others wait at the synchronization point. If you're using pipeline parallelism, PP, where the model's split up like an assembly line, chunk A creates what's called a pipeline bubble. Stages downstream just sit idle. These effects combine. They lead to reported slowdowns of like 1.3x to 1.4x, even for context lengths we don't even consider that long anymore.
Okay, so researchers obviously tried to fix this load imbalance. What was the first idea? Variable length chunking. Instead of fixed 4K chunks, they tried to shuffle documents around to make the total quadratic compute load more even across devices.
Right. But that approach ran straight into a classic parallel computing problem. Balancing the compute load often unbalances the memory load. To get compute perfectly balanced for a really large context, like 512K tokens, you might need to move documents such that some devices suddenly need, say, 1.1x or even 1.2x more activation memory.
So you fix the compute imbalance but create a memory imbalance, pushing some GPUs over their limit.
That's the issue. Anyone who's trained these models knows that feeling of just hitting the memory ceiling. This attempt at balancing pushes some devices right to that edge. And that leads to GPUs sitting idle a lot of the time. We're talking up to 55% idle time in certain DP setups. Just wasted potential.
So if balancing the data chunks didn't quite work, what came next? Context parallelism.
Yeah, context parallelism, or CP. This was clever. Instead of moving whole documents around, it slices the document itself along the sequence length. So each device gets a piece of the sequence. In theory, this should balance both compute and memory pretty well.
That sounds like a really good solution. Why isn't everyone just using CP then?
Well, it turned out to introduce 3 new, pretty significant bottlenecks, especially when you scale up. First is the tiny shards problem. If you slice up a short document, the pieces can be too small for the GPU kernels to run efficiently. Performance really drops for documents under maybe 128 tokens. Second, and this is a big one, communication cost. CP needs this operation called all gather to pull together the key value states, the KV cache, from all the shards. As you scale up your training job, going from maybe 2 nodes to 32 nodes, the time spent just waiting for that all-gather communication, it balloons from maybe 3% to nearly 40% of your total time per step.
Wow, 40%. So as you add more computing power, you end up spending almost half the time just waiting for data to move around.
Pretty much. The system spends more time talking than working.
Yeah.
And the third issue is related, KV memory pressure. Because the computation is sharded, the very last device in the CP group has to hold on to the entire document's aggregated KV states for the backward pass. That memory usage grows too, from maybe 3% on 2 nodes to almost 30% on 16 nodes. Again, limiting how big your context can realistically be.
Okay, this really sets the stage for core attention disaggregation, or CAD. The idea seems to be if that quadratic attention part is the troublemaker, let's just pull it out. Separate that core attention compute, the softmax QK-top VWeb bit, from all the other layers. Let it be scaled and scheduled on its own.
Right. And CAD is possible because of two really neat properties of that core attention or CA function. First, it's stateless. There are no trainable weights in there. It's just raw computation figuring out token relevance. Since it's stateless, the load balancing problem becomes much simpler. It's just about scheduling compute tasks efficiently. Second, it's composable. You can chop up that CA calculation at the token level into smaller pieces, these arbitrary length shards they call CA tasks. And crucially, you can then rebatch these small tasks together into one big, efficient kernel operation, as long as their lengths are multiples of 128 tokens. Gives the scheduler a lot of flexibility.
And that flexibility gets used in their system, DistCA. It's like creating a specialized crew just for the heavy lifting of attention. These CA tasks get sent off to independent resources they call attention servers.
And DistCA uses some smart tricks to make it work well. One is the in-place attention server, basically a GPU timeshares. Sometimes it's through the normal linear layer stuff. Other times it temporarily acts as an attention server for other GPUs. This keeps all the GPUs busy and maximizes memory utilization. Another key piece is ping-pong execution. This is how they hide that communication cost we talked about. Microbatches get split into smaller ping and pong nano batches. While the system is sending the Q, K, V data needed for the pong batch, the GPU is busy computing the attention for the ping batch. So the communication for one batch gets hidden behind the computation of the other.
That sounds like really intricate coordination. Needs a smart system managing it all.
It does, and that's the final piece, the communication-aware greedy scheduler. The scheduler is the brain using a quick rule, a heuristic, to decide how to partition the CA work and which attention server gets which task. It tries to minimize the communication needed for the computation it sends off, keeping the attention servers balanced while also reducing the overall data movement.
All right, let's get to the results. Because they tested this DistCA system on some serious hardware. Llama 8B and 34B models, context up to 512K on up to 512 H200 GPUs. What did they find?
Well, the headline result really validated the whole approach. DistCA improved the end-to-end training throughput by up to 1.35 times compared to the best previous baseline systems. This was specifically for the AB model with a 4D parallelism setup. It strongly suggests that load imbalance really was the main thing holding back performance.
And did that ping-pong communication hiding thing actually work in practice?
It did. They did an ablation study, comparing it to a theoretical case where communication cost was almost zero. DistCA with ping-pong achieved nearly the same latency. It means that communication overhead, which could have added 10–17% latency, was almost completely masked. And that smart scheduler, it showed its value in managing that compute memory trade-off. For the bigger 34B model, they actually allowed the scheduler a little bit of leeway, a tolerance for compute imbalance, up to about 15%.
Why let it be imbalanced on purpose?
Because allowing that small amount of imbalance actually reduced the communication memory needed by 20–25%. And critically, it did so without making the overall time per step any longer. It's about finding that sweet spot. Don't schedule so tightly you cause tons of data movement, but don't schedule so loosely that stragglers slow things down. They optimize the whole system.
So wrapping this up, core attention disaggregation seems like a really potent architectural fix for this fundamental load imbalance problem in long context training. By isolating that quadratic attention workload and managing it separately, CAD enables much smarter scheduling than previous methods that were kind of stuck between balancing compute or memory. It's strategic scheduling, not just packing.
Right, and maybe a final thought for you to consider here is how the system design itself changed. Think about that time-sharing GPU, switching roles between being a general compute unit and a specialized attention server. That's more than just load balancing. It's fundamentally rethinking how we use these parallel resources, maximizing their utilization in ways that could really push the boundaries for future large-scale AI training.